Hi everybody, my name is Sergey Melnikov and I am CTO or Chief Technology Officer for Corporate and Investment Banking at Raiffeisenbank. Raiffeisenbank of Russia is a representative of big Central European banking group called Raiffeisenbank International with head office located in Vienna, Austria. Raiffeisenbank is a bank with great legacy and more than 1.5 century history. Initially, I wanted to tell you about investment products for corporates, products like bank guarantees, factoring, loans, deposits, and all their features and differences. But suddenly I realized there is no point to tell about that here. Actually, I want to tell you as a regular engineer, programmer, developer, whatever you call that, and share some case studies. Case studies about one area of math which is hidden actually everywhere, from quantitative trading to compilers. It's used everywhere from hedge fund to game development company through, of course, enterprise development. This area of math is fundamental and could be found at any area. It's graph theory. I wouldn't tell you about simple applications like social graph analysis or branch distribution, or maybe sometimes flow maximization over network. Let's discuss really something interesting and important. Let's imagine we're going to introduce some new product for private individuals. And this product purpose is to help people invest their money to proper assets and as a result earn additional money in comparison to bank deposit. There are a lot of asset classes and different assets within any class which we could use and advise to invest. And the question here is to how to choose the right assets in order to maximize profit while minimizing profit variation. And actually, it's quite challenging task, and we are constantly doing experiments with new approaches. And one of these approaches is network-based asset allocation. This approach uses coefficient of correlation between assets prices for building time-varying network. Actually, you can calculate correlation between any two assets. So it has no point here to build a graph with all possible edges. So the key idea here is to use some suitable subgraph with limited number of edges based on correlation on assets prices. And graph theory helps us to understand which subgraph to use. For example, in a research, there was an analysis and comparison of types of subgraphs like minimal spanning tree and the others. So graph theory inspire us to invent new approaches for building portfolio and understand which particular assets to use at our portfolio. And of course, help our customers to earn additional money. And as we decided our asset allocation strategy works, it's time to start implementation for production run. Typically, complex applications uses dependency injection frameworks. Those frameworks simply simplify dependency management and let us to write code without strong dependencies between packages or classes itself. So during application start, the dependency injection framework should provide actual dependencies instead of dummy ones. This process is called dependency resolving. For that, dependency injection framework builds dependency graph. And as a dependency graph is built, framework starts to go through all nodes and initialize them. And suddenly it's implemented as topological sort of dependency graph. Actually, it's how Spring Framework works, and I strictly believe it's must-known knowledge for any developer. Knowledge how dependency resolving works in a nutshell, and to understand the true reason for issues or errors during dependency resolving. And it's again graph theory. So next task is to make our software to be as fast as possible, as fast as necessary. Nowadays, the only way to get significant improvement of performance is an explicit parallelization. Of course, I'm talking about throughput optimization, not latency optimization. So our software should utilize as much CPU cores as possible. which means our software should work in parallel or concurrent model. Usually concurrency isn't an easy thing to do, and the difficult thing here is that most of concurrent data structures and algorithms have their own trade-offs. It's relevant, of course, for single-threaded data structures and algorithms, but for concurrent ones, there are way greater number of dimensions to deal with. And as a result, standard language library does not have concurrent data structures or algorithms which fits everybody, especially us. So quite frequently, we have to develop new data structures and algorithms which perfectly fits our own needs. Let's imagine we have developed some new concurrent data structure which fits our own needs. Additionally, difficulty here is to validate if with the concurrent data structure works properly as we intended. And actually, there is Java memory model for software written in Java or any other JVM-based languages like Kotlin or Scala. And of course, most of our software is written in Java. Java memory model provides strong background of guarantees how our code will be executed in concurrent mode. And since Java memory model gives us that solid background, we could use that for algorithms verification. Java memory model let us to represent all statements at our code as graph. And if there is some guarantees between two statements, those statements will be connected with happens before edges. And there is no data races between two statements if and only if those two statements are linked with happens before edge. So in order to validate algorithm or maybe a new data structure, we have to draw statements graph and check if there is such edges between graph nodes. Suddenly it's graph theory again. Let's go deeper. After verification of a new algorithm, graph theory is still in charge. When we compile our code, compiler frontend uses graph representation in order to verify type safety. And moreover, register allocation phase during so-called intermediate representation lowering is done as graph colorization case. So by the time we have production run for our brand new product, we have already used graph theory a lot of times. Graph theory inspired us to build graph for assets and to choose a proper subgraph of them. Graph theory helps us to write dependency-free code and improve sustainability of this code in future by using some dependencies. Graph theory let us to validate our concurrent data structures or algorithms. And even if we have not noticed that, graph theory is widely used at infrastructure software like compilers or virtual machine. So graph theory is used as a whole stack of modern IT finances, from the most low-level stuff like register allocation to the finance itself like portfolio allocation. And I strictly believe that graph theory is must for any developer. I do hope that examples of graph theory would inspire you to pick up a graph theory textbook after that competition. So, and now let the competition to be started and good luck. Bye.